All right, it's 5:30. Let's go and get started. Good evening, everyone. How's everyone doing today? Good, doing good. It's drier today, which is good. Hopefully it stays that way, but I think probably we might still have some more rain. Okay. So today, I think last time we met up on Tuesday, we were in the middle of an example, so we're going to finish that up. It's gonna be a 2D truss example, and I have one more example for that to show you guys. And then after today, you should be able to do all the problems on the homework. So, because if you notice on the problem set, problem 2, or excuse me, problem 3, is all 2D problems, and so they're all going to be just like the example that we're going to finish up today and the other example. Okay. So after today, you should be able to do all of that and finish that up. All right, and so just like I mentioned, let me write it down here just so you can see. I did push the due date for homework 1 back. I finally remembered to actually put it in the put it on Canvas. And so I actually pushed it back by about 5 days, and so it's going to be due a week from today. Right, and so if you go on the Canvas site, you'll see that the due date for that has been pushed back a week. Okay. Just because it's I usually like to give you guys a week. I mean, at this point, you should be able to do most of the homework assignment, but we're technically finishing all the content for the homework today. So I'd like to give you about a week to do that stuff. So I'm giving you until 2:15 at 11:59 p.m. Okay. I literally remember to do that right as I ran out of the office, so I only changed it on Canvas. And so if you download the PDF file, it'll still say this Sunday, but it's actually due on the 15th. So I just have to go in and change the PDF file for that. Okay. All right. I think that's it for my announcements. Not much to say. Are there any questions I can answer before we get started? Okay. All right, so let's go ahead and pick up where we left off on the example. So I'm just going to scroll up here, and so this should be in your notes from Tuesday, so you don't have to rewrite any of this down. I'm just kind of scrolling up just to kind of refresh your memory. Okay, so on Tuesday we are doing this example. It's a 3-element example. So we have 2 truss bars and 1 spring. Okay, they're arranged in a 2D configuration, and what we're interested in is the deformations of node 1. Okay, so node 1 is the only node that's not fixed in this situation. All right, so for the two truss bars, we are given its material properties as a Young's modulus of 30 times 10 to the 6 psi. Its cross-sectional area is 2 inch squared, and they have a length of 120 inches. Okay, and element B is a spring with a spring constant of 250,000 pounds per inch. All right, and so to solve this problem, we are going to go through our direct stiffness method, and so the same one that we've been doing for our 1D problems. The biggest difference here is that our element stiffness matrices are going to be a lot more complex, just because we're in 2D. Okay, and so on Tuesday we went over this 2D element stiffness matrix. Okay, so we have a bunch of sines and cosines. And we're going to write this out for all 3 of the elements. And so we did it here for element A, element A is angled 90 degrees with respect to the horizontal. Okay. And we end up with this element stiffness matrix here. Okay. So we have 5 times 10 to the fifth out on the outside. And we have a bunch of zeros and ones because cosine of 90 degrees is 0. Okay. Okay, so let's go ahead and pick up right where we left off here. So let's go ahead and compute the element stiffness matrix for element B. Okay. So let me just draw the spring here, just so you can kind of see. Okay. So this is node 1, this is node 3. Okay. All right, and then this angle right here that we're given is 45 degrees. Okay. All right, so you can see from the figure here that the angle that this element here makes with the positive x-axis is 45 degrees. Okay, so that tells us our theta here is 45. Okay. So remember, when you're doing these 2D problems, it's always good to compute cosine and sine of the angle. Actually write it down next to the thing, just so that you don't have to kind of keep putting this into your calculator. Okay. Okay. So first we have cosine. So cosine of 45 degrees. This is √2/2. Okay. Then we have sine. So sine of 45 degrees. Also √2/2. Okay. All right. So let's go ahead and insert this into our element stiffness matrix. Okay. And so our element stiffness matrix for element B. Okay. First thing we're going to do is we're gonna put the stiffness of the element out in front. And so this element here has a spring constant of 250,000 pounds per inch. Okay. And so that's going to be a 2.5 times 10 to the fifth. Okay. And then we're going to start writing in our sine and cosine terms. Okay. All right. So I'm gonna use the trick that we went over at the end of class last time to kind of save us a little bit of time. Right. So remember the trick that we talked about last time was to take advantage of the fact that our element stiffness matrix was symmetric. Okay. So every time we write a row, I'm just going to write that into a particular column. Okay. All right. All right. So don't write this down just yet because I'm just writing this down here just to kind of jog your memory here. Okay. So our first row in the matrix, we have cosine squared, cosine times sine, minus cosine squared, minus cosine sine. Okay. So let's plug these in one by one. So first we have cosine squared. So cosine squared is going to be √2/2 times √2/2. You multiply those two things together, you get 2/4. 2/4 is just the same as 1/2. Okay. All right, next we have cosine times sine. Both sine and cosine in this case are √2/2. So we have √2/2 squared again, which is going to give us 1/2. Okay. Then we have a minus cosine squared. Cosine squared we know is 1/2. We add the minus sign there, it's going to be a minus 1/2. Okay. Then we have a minus cosine times sine. And we do the math again, we end up with a minus 1/2. Okay. Okay. So now that we've written the first row in the matrix, we know that we can just copy those entries from the first row and kind of rotate that down into the first column. Okay. So I'm going to write the first column at the same time. All right. The first thing we're going to rotate over is this 1/2. So that's going to put a 1/2 in the second row of the first column. Okay. Next thing we're going to rotate over is the minus 1/2. So we're going to have a minus 1/2 here in the third row of the first column. And then one last one we're gonna have a minus 1/2 in the fourth row of the first column. Okay. So definitely make use of this trick here. It does save you, it seems like it doesn't save you time because I'm explaining it, but once you kind of get used to it and you start using it, it does save you time. Especially when you have element stiffness matrices that don't just are comprised of zeros and ones and 1/2s. Right? So this is actually really useful for when you have a theta of like 30 degrees or 60 degrees, because then you're gonna have a lot of different terms. Okay. All right. Any questions on this so far? Okay. All right. So let's go with the second row now. So the good thing about this method is that we already have the first entry of the second row already written, and so we only have to worry about the last three entries. Okay, so our last three entries here are sine squared minus cosine times sine and minus sine squared. Okay. So let me just go ahead and plug in for these. So sine squared is going to be 1/2. Okay. Minus cosine times sine, that's going to be a minus 1/2. And then minus sine squared, this is going to be a minus 1/2. Okay. Once again, we're going to use our trick. And so we're going to write these into the remaining entries in the second column. So this one here is going to be a minus 1/2. And this one here is going to be minus 1/2. Okay. All right. So that's the second row. Now let's do the third row. Okay. And as you get further and further down, it gets easier. Okay. So this is going to be a cosine squared and a cosine times sine. Okay. Both cosine squared and cosine sine are going to be 1/2 in this case, because they're both just √2/2 times √2/2. Okay. We're going to have a positive 1/2, positive 1/2. Okay. We're going to do our trick. And so we're going to write that last entry into the third column. Okay, so it's going to be 1/2 down there. And then our last entry here in the bottom right is going to be sine squared. Okay. And we know sine squared is going to be √2/2 times √2/2, which is also just 1/2. Okay. All right. And then last thing we're going to do before we move on to element C is we're going to write the degrees of freedom that this element stiffness matrix is responsible for. So we know from this figure here that element B is connected to nodes 1 and 3. So that means we're going to have D1x, D1y, D3x, and D3y. All right. Any questions on how we got that? Okay. All right. So let's keep going. So we have one more element here. We have element C. Okay. So element C looks like this. 1, 4. Okay. So you can see here we have a perfectly horizontal element. And so since there's no angle here, it's perfectly horizontal, our theta here is just going to be 0 degrees. Okay. All right, so if we compute our trig terms here, cosine of 0 is going to be 1. And then sine of 0 is going to be 0. All right, so let's go ahead and plug all these in. This one's a little bit easier just because we have some zeros. And so we know that any term that involves sine in our element stiffness matrix is just going to go to 0. Okay. We already computed the quantity AE over L from the previous back on Tuesday. That was 5 times 10 to the 5th. And so I'm just going to include that one there just like that. Okay. And so if we put these in, I'm just going to do this quickly just because this one's much simpler. So our first row is going to be 1, 0, minus 1, 0. We write that into the first column, right? We have something that looks like this. Okay. There's a matrix just like that. All right, so now we go to the second row. So the second row has all terms that involve signs. We're going to have 0, 0, 0. Okay. And then those last two entries in the second row, we're gonna write those into the remaining entries in the second column. All right. And so the third row, we start with a 1 and then 0. That 0 comes down here. And then lastly, we have a 0 in the bottom right of the matrix. Okay. And so last thing, let's go ahead and indicate which nodes that this is connected to. So this is D1X, D1Y, D4X, D4Y. Okay. Because element C is connected to nodes 1 and 4. All right, so all of our element stiffness matrices are done. We're ready to move on to the next step in the direct stiffness method, which is assembly. All right, so it's for these problems that you may be interested in using a spreadsheet program or some kind of a program online just to kind of help keep track of the matrices. Because this can get gnarly. Okay. Okay. So in this particular problem, we have 4 nodes, right? Labeled 1 through 4. But since we're in 2D, each node is going to have 2 degrees of freedom. Because each node is it's possible to deform in the x direction and the y direction. Right, so what does this mean for our global system, right? So if there's 4 nodes in the system and each node has 2 degrees of freedom, that means our global system is going to be an 8 by 8 matrix. Which is going to be by far the biggest matrix we're gonna write here right here in this class. Okay. So it gets messy, and so I'm lucky because this is over the course of my lifetime, this is probably the 11th time I've done this problem in front of people. So I know what the solution is, but if you're doing this for the first time, it gets very easy to kind of get lost. Okay. All right, so let's start with the forcing vector. So the way this works is that you're going to go node by node, starting from node 1 to node 4, and you're going to list its x and y components. We have f1x, f1y, f2x, f2y, f3x, f3y, f4x, f4. 8 rows. Okay. And so our matrix similarly is going to have 8 rows and 8 columns. Okay. Oh, I forgot one thing. We're going to do that thing where we kind of make things simpler. So let's have a factor of 10 to the 5th out in front. Okay. Just to save ourselves a little bit of writing. So it's implied that everything inside the matrix is going to be multiplied by 10 to the 5th. Okay, so let me go ahead and write the columns in here. I think for this problem, it's especially useful just because there's so much going on. So we have D1X, D1Y, D2X, D2Y, D3X, D3Y, D4X, D4Y. Now we're going to write the rows in. So we have D1X, D1Y, D2X, D2Y. All right. Okay, so the next step, of course, is to write in or to slot in the element stiffness matrices in the appropriate location. Okay. And so in a lot of ways, this mimics what we had in the 1D problems. There's just kind of more stuff to keep track of here in 2D. Okay. All right, so we're going to start with element A. And so we know from the diagram that element A is connected to nodes 1 and 2. Okay. All right, and so this one's actually the easiest one because node 1 and 2 are next to each other in the matrix. And so we're just going to kind of highlight this kind of 4x4 block. Okay. So we're going to grab all of those columns there, all of these rows here. Okay. And so we have kind of one contiguous block just like that. Okay. Okay, so let's write in the entries for this element. Okay. So this is the matrix that we came up with last time. It should be 5s. Because we only pulled out a 10 to the 5th. Okay. Remember that A over L in front of the matrix, that's 5 times 10 to the 5th. If we're only going to pull out a 10 to the 5th in front of the entire matrix, that means all of those have to be 5s. Okay? And they're in those locations, just based on the matrix. Okay. Okay. So that's element A. Now it's going to get a little bit tricky because the elements or the nodes are no longer going to be next to each other. And so we're going to start with element B. Element B is connected to nodes 1 and 3. Okay. Okay. So we need to identify all of the entries, all the rows and columns that have to do with node 1 and node 3. Okay. So for a 2D problem like this, what you're going to see is that our 4x4 matrix is going to split into 4 2x2 matrices. Okay. Let me show you what I mean by that. And so first thing we're going to do here is we're going to block off the node 1 section. Okay, so it's going to be this one right here. So this is the D1X, D1Y, D1X, D1Y section. Okay. Okay. Next thing we have here is the D1X, D1Y, D3X, D3Y. So that's going to be this section here. Same thing for the other direction. So we have D3X, D3Y row, D1X, D1Y column. That's going to be this one here. And then we have the D3X, D3Y row, D3X, D3Y column. It's going to be this one right here. Right. And so if you're wondering how to split this up, let me just kind of scroll up here just so you can see. Okay. So right here we have the element stiffness matrix. So all I did was kind of split it up into 4s. Okay. And so this upper left quadrant here, this goes in the upper left quadrant of the blue in the big matrix. So I've basically taken those four quadrants and kind of split it up into the different parts based on the node number. Okay. Okay, so let's go ahead and insert these. Right. So remember, for any overlapping components, we're just going to add them together. So we're going to add a plus. Well, and the numbers for this are a little bit unfortunate because in front here we have a 2.5 times 10 to the fifth. And so we take 1/2 of that, we get 1.25. Okay. So we have plus 1.25, plus 1.25, plus 1.25, and this 5 plus 1.25. Okay. Right, so for all of those overlap, we're going to add a positive 1.25 to them. Okay. All right, so now we're going to go to the upper right. And so the upper right, that blue portion is going to be all negative. So we have a minus 1.25, minus 1.25, minus 1.25, and then minus 1.25. Okay, then we come to the bottom left. So the bottom left, we have a minus 1.25, minus 1.25, minus 1.25, minus 1.25. Okay. All right, and then we come to the bottom right, which is a positive 1.25, 1.25, 1.25, 1.25. Okay. All right, any questions on this so far? It's very tedious, I know. It's a lot to writing. If you took 410 with me last semester, this should look familiar to you, but it's probably not a happy memory. I will say that the reason this is so tedious is that, remember, these algorithms for finite elements, these were designed for computers to do, and if computers are good at any one thing, they're very good at very tedious, repetitive processes like this, and so that's why it's kind of like this. But when you're doing it by hand, it's just kind of annoying. Okay, but we only have one more element to go. All right, so that's element C. So element C, as we know, is connected to nodes 1 and 4. Okay. So let's go ahead and highlight those locations here. Okay, so first one we have here is D1X, D1Y, D1X, D1Y. That's going to be this upper left portion here. So that portion there is getting very crowded. Okay. Next, we have the D1X, D1Y, the cross term with the D4X and D4Y. Okay, so that's going to be the very top right of the global matrix. Right, and then if we fill in the other portions, they look just like that. Okay. Okay. So let's go ahead and add these in. So luckily, most of these are 0. Okay. We're gonna have a +5 here on the top left entry. Okay. Then we have zeros for everything else. I'm just not going to bother writing the zeros. Okay, so we have -5, 0, 0, 0, and then -5, 0, 0, 0, and +5, 0, 0, 0. Let me clean up the terms here on the top left, just so it's easier to read. Okay, so top left right here with the 6.25, 1.25, 1.25, and 6.25. And of course, everything that's not boxed, just like we did in the 1D case, is just going to be all zeros. All right. Any questions on this so far? All right, so now that we're done with assembly, the next step is going to be the boundary conditions. All right, so let's take note of all the boundary conditions that we see in our matrix, or we see in our situation. All right, so first thing is we have fixed constraints, and so these are locations where the structure is fixed to have zero deformation. Okay, we have these on 3 nodes, and so this is going to be on nodes 2, 3, and 4. Right, and the other boundary condition we have is that we have a force of minus 10,000 pounds because it's going in the downward direction. And that's going to be applied on node 1. Okay. Okay. So let's go ahead and apply all of these conditions here. Okay. All right, so let's start with the fixed constraints. Okay. So this is applied on 3 nodes, but remember, each of these nodes here have 2 degrees of freedom, right? Both the X and Y displacements. And so we have fixed constraints on 3 nodes, but that's actually going to knock out 6 rows in our matrix, okay? So everything involving nodes 2, 3, and 4 are all going to be zeroed out. Okay? So that means this one's going to be 0, this one's going to be 0, this one's going to be 0, 0, 0, 0, okay? And we need to make the corresponding changes to the row as well. Okay. And so for the F2X row, I'm deleting a bunch of zeros just so I can write zeros back in there. Because I'm a genius, I guess. But it's also a different color, so you can kind of see the changes that I made. Okay. Okay, now we're going to do this for the F2Y row. So again, we're going to delete all of these entries here. Replace most of them with zeros, except for the main diagonal. Okay. And so since this is the 4th row in the matrix, we're going to make the entry in the 4th column equal to 1. Okay. Okay, and then we're just going to keep repeating this for every row. I'm not going to erase all the zeros. Just, and so this is the time when people usually ask, maybe not out loud, but in their mind, maybe accompanied with a few curse words. And so, why did we go through all that trouble of assembling this matrix if we know that all those rows are going to be zeros and ones anyway, right? And so you're right. And so if you do have that foresight and you know that the matrix is going to end up this way, you could do that. You just just kind of be careful taking those shortcuts because you don't want to miss, I think what happens sometimes that people kind of, they take these shortcuts and they forget to add an entire element stiffness matrix. Okay. Because for this particular problem, we did end up deleting most of this matrix. But those first 2 rows, the rows that have to do with D1X, D1Y, all 3 elements are contributing to them. And so if you miss one of those elements because you thought like, oh, the nodes are fixed, you're going to miss the result by quite a bit. Okay. And so maybe, maybe you could do something in between. Maybe you just write those parts in and then the other parts you don't really bother adding in. That's fine too, right? You guys are grad students. And so, you guys are all adults, I feel like I don't have to hold your hand through this, at all. So do what works for you. Just just be careful. Just be careful doing this kind of thing. Okay. All right. So that's all the Dirichlet boundary conditions. That's all the constraints. Okay. Next, we have our Neumann boundary condition, which is our load. And so that is a load of minus 10,000 pounds. Okay. And that's being applied in the y direction on node 1. And so we're going to replace F1y with that. Okay. And then for F1x, we don't have any force that's in the x direction on node 1. And so we can just replace that with a 0. Okay. All right. So after lots of writing, we finally arrived at our matrix here. Okay. And so at this point, you would plug this into MATLAB and then use it to solve for the solution. Okay. Any questions on how we got to this point here? Okay. All right, so let's go ahead and punch this into MATLAB. Well, technically the me from 4 years ago punched this into MATLAB, but we'll take credit for it all the same. All right, so if we punch this in, we get d1x is equal to 0.0033 inches. Okay. d1y is a minus 0.0167 inches. Okay. Technically, when you solve this system, you're going to get the values for d2x and d2y, d3x, d3y, d4x, d4y, but they're all going to be zeros because of the constraints. Okay. All right. So that's the example. It took us almost half of the entire lecture. Not because, again, not because these problems are hard. It's just a lot of writing to do. Okay. All right. Any questions on this before we move on to the next thing? Yeah.
So it's just going to go to the right and down?
Yes, exactly. Yeah. Yeah. Which is interesting because our force is only in the y direction here, right? But we do see a little bit of drift over to the right, and that's mostly just because of the spring. And so, and when the spring kind of pulls down, it kind of, it has to kind of lengthen in that direction. So it kind of pushes it over to the right. Okay, so let's go ahead and move on to the next thing, which is it's actually kind of an addendum to this example. Okay, because one thing that you can do for truss elements is you can compute the stress in the truss elements. Okay. And so when I talk about stress, what I mean is kind of internal structural stress within the element. Okay. So the reason I'm bringing this up is that when we do ANSYS in a couple weeks, one thing you're going to learn is that a lot of people use ANSYS to do stress analysis. Okay. FEA. Okay. In industry, that's one of the main things that it's used for. And the reason it's used a lot is because if you're going to do failure testing, right? If you want to make sure that your structure is going to hold up, if it's going to support its weight, support its load, one way to do this, or one of the main ways to do this, is to make sure that your internal stress does not exceed the strength of the material. Okay. So this is a lot more prominent in kind of I would say kind of practical FEA. But I do want to show you that you can actually compute this with our kind of our simple direct stiffness method here. Okay. Okay. And so to do it in a truss bar, we kind of take advantage of the fact that what we assume is that all of the forces are just acting purely axially down the element. Okay. And so the stress is going to be nothing more than just the local force. Okay. So remember remember this hat notation. So the hat notation means that it's parallel to the element, okay, divided by its cross-sectional area. Okay. So this is the axial force, and this is the cross-sectional area. The good news is that after you complete a direct stiffness problem, so let's say that you just did the previous problem there, you have access to all these pieces of information, although we do have to kind of work on it a little bit. Okay. So it does involve some transformation matrices, and in the interest of time, I'm going to skip the derivation for it, but it's the solution that looks something like this. Okay? So if you want to compute the stress in a particular truss element, what you would do is you take the Young's modulus divided by the length. You're going to multiply that by a row vector. Okay? So this row vector is going to be minus cosine, minus sine, cosine, and sine. Okay. So you can see here we have our sine and cosine terms. So these are element specific. Okay. And then you're going to multiply that by a column vector of that element's deformation. Okay. Okay. And so this does require you to kind of pick out different entries of the solution. Okay. For that particular element. So I'm going to show you how to do it for both of the truss elements in the previous examples, just so you can see how this is done. Okay, so let's take our result from the previous example and let's compute the stress. Okay. Okay, so let's start with element A. So element A is the first truss bar that we have. It's the vertical one. So if we come back up to this figure here, we see element A is connected to nodes 1 and 2. It's the one that goes up and down. Okay. So this is nodes 1 and 2. Okay. All right. We also know the angle here. So the angle here is 90 degrees. That means cosine is going to be 0 and sine is going to be 1. Okay. So the stress in element A is going to be the Young's modulus divided by the length multiplied by this row vector. We have minus cosine. Minus cosine is going to be 0. Then we have minus sine, minus 1, 0, 1. Okay. Then we're going to multiply this by by the deformation vector for that particular element. Okay, so this is going to be a 4 by 1. So it's going to be d1x, d1y, d2x, d2y. Okay, some of these can be 0. That's okay. Okay? And in fact, in all likelihood, some of these are going to be 0 because of the fixed constraints. Okay? So let's go ahead and plug in for these. And so we have a 0.0033 inches for d1x. d1y is a minus 0.0167 inches. And then d2x and d2y are both 0. Okay. All right, so then we do the vector multiplication. We have a row vector multiplied by a column vector, so that's just going to be basically just the dot product between those two vectors. Okay. We plug in for E, we plug in for L, and what we get is 4,175 PSI. Okay. Okay. So the magnitude is important, but one thing we can also get from this is the sign, right? And so since this is a positive 4,175, this tells us that this element is in tension. Okay. So, we're going by the convention that a positive stress is tension and negative stress is compression. Okay. So let's do that one more time, but let's do this for element C. Okay. So element C we know is connected to nodes 1 and 4. Okay. And its angle is 0 degrees. And so with 0 degrees, we know this cosine of 0 is 1, the sine of 0 is 0. Okay. All right, so let's compute the stress. So we have stress in element C is E over L. We have -1, 0, 1, 0. Okay. Then we're going to multiply it by a column vector of its nodal displacements. So for nodes 1 and 4, we have d1x, d1y, d4x, and d4y. Okay, so d1x, again, is 0.0033 inches. d1y is -0.0167 inches. And both of these are 0. Okay. All right, so we multiply this out, and what we get is a minus 825 PSI. Negative. So that tells us that we are in compression. All right. And so if you look back at the figure and you look at kind of how those elements are arranged relative to the force, that makes a lot of sense, right? So remember, our force is pulling downwards, okay? And so it makes sense that element A, which is kind of vertically upwards, that element would be in tension because we're kind of pulling it away from its support, okay? Whereas element C is a horizontal one, right? We do have a very small deformation. It's an order of magnitude less. We have a little bit of deformation going to the right because of the action of the spring, right? And so it makes sense that this element would be in compression. Okay. All right. Any questions on this here? Okay. All right. So let's do another example. All right, so this is it's gonna be a little bit shorter just because we've kind of gone through the whole process now. So let's look at a 2-bar assembly. So we're gonna have one element that kind of comes down just like that. Another element that's going to be coming across just like that. we're going to introduce another kind of support here, one that we haven't seen yet, called a roller support. Okay. All right, so we'll talk about how to deal with that in terms of the boundary conditions. Okay. All right, so let's go ahead and label these nodes. So we have node 1 here is on the right. Node 2 is going to be the one that's up top. And node 3 is going to be here on the left. Okay. We'll go ahead and label this node element A up top and element B on the bottom. Okay. The angle in between the two elements we're going to assume is 30 degrees. Okay. The length of element B is going to be 5 feet. And then the length of element A, we're going to assume is 10 feet. Okay. Besides that, we're going to assume that both of the truss bars are going to be made of the same material. So they're going to have the same Young's modulus, and we're going to assume that they have the same cross-sectional area as well. So we have E is equal to 30 times 10 to the 6th psi. All right, question. So how would a hinge support differ from a fixed support in our calculation? So so all of these, because these are truss elements, we've mostly just been dealing with hinge supports or pin supports. Effectively, they're the same thing as a fixed support, just because of the truss bars don't impede rotation at all. But what you're going to see once we get to beams, the beams do have a difference between pinned and fixed supports. If you mean the roller support, that is going to make a difference in terms of how we constrain the different degrees of freedom. But I'll leave that until we get to the boundary condition portion. Yeah. If you want a very quick answer, we're going to constrain one direction, but we're going to leave the other one free. Okay, and so our cross-sectional area is going to be 1 inch squared. Okay, so just like we did in the previous one, let's use our direct stiffness method. To compute deformation. Okay. Any questions on this problem setup here? Okay. Oh, question? Question. So I was wondering how we would apply a torque constraint for a fixed support since we're only dealing with the force matrix. Yeah, it's a good question. So we'll be dealing with torques when we get to beam elements, and so that's going to be the next element type. So for trusses, we're only considering just linear forces and linear deformations, just because we assume the truss can only be able to compress and expand. But for beam elements, we're going to consider transverse deformation. So a deformation that's perpendicular to the axis of the element, as well as rotations. And so when you add rotations as a degree of freedom, then you can add torques as a force as well. Yeah, that's in literally the next section. So after this example. Yep. Okay. So let's start with the same method as we did before. So let's start with our element stiffness matrix. So we only have to do 2 here, which is nice. And so let's start with element A. So let me draw it here just for the sake of I know I have it right up there, but let's draw this one here. Okay. All right, so from the figure we know that element A is connected to nodes 1 and 2 in the configuration shown. Okay. And we're also given this angle right here, which is 30 degrees. Okay. So we now need to compute the element stiffness matrix for this element. Okay, so the first question we're going to answer is what is the angle theta for this element? Okay, it's very tempting here to put 30 degrees, right? Because that's the angle that's given to us in the figure. But I'm going to tell you just to kind of hold your horses a little bit, because remember what this angle here is defined as, right? This angle here is defined as the angle between our element and the positive x-axis. So where is the positive x-axis in this situation? Well, there is not one, but we have to draw one in. Okay? And so what you have to do in these situations is you have to go to the lower numbered node. Okay? Which in this case is node 1. Okay, so node 1 is the lower numbered node in this case. And then from there, you're going to draw the positive x-axis. Okay. All right. So now what we want is we want the angle between this element and that positive x-axis. So the angle that we actually want is this kind of larger angle like this. Okay. And so we do a little bit of a geometry here. We can see that this angle here is actually 150 degrees, not 30 degrees. Okay? And so the angle that we actually want to plug in here is actually 150 degrees. All right, so why do we use this convention? Why do we use the lower numbered node? Why do we use the positive x-axis? You know, in honesty, there's not a great reason for it. It's just a convention. And so, you know, in order just to make sure that when you do these problems, you're consistent and everything kind of lines up correctly, you know, we have to have a convention. And this is just the one that I use. And so you can very easily choose a different convention. So if you want to use the higher numbered node, you want to use the y-axis, or if you want, you can do all that. And so as long as you're consistent in your convention, you're going to end up with the same answer. But, you know, if you want to just kind of follow the same method, this is the one that I use. So I use the positive x-axis on the lower numbered node, and I rotate counterclockwise from there. Okay. So let's compute the cosine and the sine of the angle. So cosine of 150 degrees is a minus √3/2, and sine is a 1/2. Okay. So unfortunately, this is going to make things a little bit messy for our element stiffness matrix, and so our trick from earlier is going to help tremendously. Okay. Okay. So let's write in the element stiffness matrix Ka. Okay. Oh, by the way, the AE/L, let's go ahead and compute that now. Okay. So if you plug in all of the values for AE/L, you get 2.5 times 10 to the 5th. Okay. All right, so out here we have 2.5 times 10 to the 5th. Okay. Multiplied by our element stiffness matrix. Okay. Okay, so things aren't going to be as uniform here, and so it's actually going to be a little bit of a hassle to do. Okay, so on the top left, we have cosine squared. So cosine is negative √3/2. So negative √3/2 squared is a 3/4 positive. Then we have a cosine sine. So then that's going to be minus √3/4. Okay. Then we have minus cosine squared, which is a minus 3/4. And then a minus cosine sine, which is going to be a √3/4. All right. And we're connected to nodes 1 and 2. So it's d1x, d1y, d2x, d2y. Okay. All right, so let's go ahead and write this into the first column. This can be a minus √3/4, minus 3/4, √3/4. Okay. All right, then we have the next row, so it's gonna be 1/4, √3/4, minus 1/4. Okay. All right, so just for the sake of time, I just went ahead and just filled in everything there, but definitely you can go ahead and go back and kind of re-verify all these calculations. By the way, for these types of problems, I'm never going to give you a weird angle, so I'm never going to give you like 47 degrees or anything like that. So it's always going to be something nice, either 0 degrees, 30 degrees, 45, 60, or 90 in those multiples. Okay? I like to think that I'm not a cruel person, although some people will disagree, but that's okay. But I like to think that I'm not a cruel person. So and that's mostly to myself. I don't want to be a cruel person to myself and have to compute all those weird angles, sine to cosine. So so you're always going to get something that's 0, 30, 45, 60, 90. Okay. Unless it's a computer. We can be cruel to computers, but not going to be cruel to people. All right, any questions on this here? Okay, so let's go ahead and do the same thing for element B. Okay, so once again, I'm going to draw the element here. All right, so we have a horizontal element, so that's good. So that means it's going to simplify our element stiffness matrix quite a lot. Right? Well, let's apply the same convention here for the angle. So we know the positive x-axis, we're gonna draw it at our lower number node. Okay. And so in order to get into the orientation that we have here, we have to rotate counterclockwise by 180 degrees. Okay. So our angle here, theta, is 180. Okay. Cosine of 180 is -1. And sine of 180 is 0. Okay. We also have the AE over L. AE over L in this case, L is half of what it was for element A. So this could be 5 times 10 to the 5th. Okay. For element stiffness matrix, the fact that we have sine of 180 is 0 is going to help us out a lot. Okay. Okay. And then we have 1, 0, -1, 0, 0, -1, 0. Okay. When you have a 0, it's nice. You can fill in most of it with zeros. Okay. X. D1x, D1y, D3x, D3y. Okay. All right, so the next step is going to be assembly. So let's go ahead and do that. We have a little bit of a more reasonable system here because we only have 3 nodes. And so that means our stiffness matrix is going to be a 6 by 6. All right, question. So I know it would be unconventional, but could we have chosen our positive x-axis to be in the opposite direction? It would yield different matrices. It would yield different matrices, but as long as you're consistent with it, all of those things are going to they're going to cancel out in the end. So as long as you're consistent, you can choose whatever convention that you want. Yeah. So you very easily could have chosen the positive x-axis to go the other way. As long as you're consistent and you calculate the angles the same way, you're going to get the same result. Yeah. The sign, and at the end, the sign might be different. So you might get like a negative x deformation, but that's because you define the positive x direction to be going to the left. Yeah. Yeah. As long as you're consistent and you kind of know to apply it all throughout, you can do all that. Mm-hmm. All right, so assembly 6 by 6 matrix. Okay. We have F1x, F1y. Thanks. Okay. Let's go ahead and insert our matrix here. Okay. What's the best way to do this? So the one that's really a pain in the ass to do is going to be element A, just because we have all these root threes and stuff going on. Whenever you have an irrational number, that's never fun to input into a matrix. And so, okay, let's do this. So first thing we know, since we have an extra factor of 10 to the fifth, I'm going to leave that outside there. Okay. Let's highlight the locations where they're going to be. I'm kind of rushing a little bit just because I do want to get to the end of this example before class ends today. Okay, so we know element A is connected to nodes 1 and 2. And it's going to take up this portion right here. Okay. Element B is going to be nodes 1 and 3. So if we box that out, it's going to be here, 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 and here. Okay. All right, so I'm just going to fill this in. Of course, you know, this requires you to kind of do each one kind of individually and then kind of add them up. But let's do this just for the sake of time. So in this top right here, we have a 6.875. Of course, multiplied by 10 to the fifth on the outside. Then we have a minus 1.08, minus 1.08. That is something I rounded because that involves root 3 over 4, which is an irrational number. Okay. Okay. So those are the first two rows in the matrix. Those are going to be the ones that's going to be most relevant. Okay. Because we know nodes 2 and 3 are constrained. Okay. So definitely make sure you get those first two rows down. Okay. Okay. Then the next row we have a minus 1.875, 1.08, 1.875, minus 1.08. Last two entries in that row are going to be 0 because you know, there's no matrix over there. Okay. Okay. And then the fourth row in the matrix goes just like that. 1.08 minus 0.625 minus 1.08, 0.625, and then 0, 0. Okay. All right. Minus 5, 0. Here it's a lot easier. So fifth row in the matrix is minus 5, 0, 0, 0, 5, 0. Okay. And then the last row in the matrix is all zeros. So 0 is all the way across. Okay, and so the last step that we need to do before we solve it is to do the boundary conditions, okay? Oh, I never gave you force. I always forget that. There is a downward force on node 1, 25,000 pounds. We'll put that in. Okay, so let's do the supports first. So that's the part that's interesting here. Okay, so first we have a fixed support. On node 2. Okay. So that tells us that the rows for F2x, F2y are going to be 0. Okay. Okay. We're going to eliminate all of these nice irrational numbers that we spend so much effort in computing. Here's the box 2, unfortunately. All right, so it's going to turn this row into 0, 0, 1, 0, 0, 0, 0, 1. Okay. Okay, so node 2 is pretty straightforward. Node 2 is clear just like that. Okay. So now let's go to node 3. So node 3 was the interesting one that we were looking at the beginning of this example, right? Node 3 is constrained by a roller support. So let me scroll back up here so you can look at the figure one more time. Okay. And so let me go ahead and circle node 3. Okay, so node 3 is on a roller, right? And so what a roller does is that a roller only constrains the direction, it only constrains the direction that is perpendicular to the wall. Okay. And so in this case, our roller wall is vertical. Okay. So that means the only thing we're going to constrain here is the x direction. Okay. The y direction, we're actually going to leave it free. Okay. And so what that means that when we come down here to the matrix, so let's write roller support. That means that only the x direction is going to be constrained in this case. Okay, so that means when we do our usual zeroing out, we're only going to constrain this row. Okay? We're going to leave the other row alone. Right. So when you have a roller support, you only constrain that one direction, right? Whereas normally, for a regular fixed support, you constrain both, but for a roller, you only just do the one direction. Okay? All right. Any questions on that? Okay. All right. So theoretically, if we did put the load in, so the load goes right here. So the load is a minus 25,000 pounds. And this is a 0. Okay. So theoretically, we're at a point now where we can solve, right? Well, technically, no, right? So I want you guys to look at the last row and the last column of this matrix. Okay? Notice how we have an entire row of zeros. Okay? And usually when you have an entire row of zeros, that means the corresponding column is all zeros as well. Okay? So that's a problem. And so if you try to solve this in MATLAB, you try to invert this matrix, you try to use the backslash operator, MATLAB will will actually get mad at you. And so this is something that you can't do. Okay. And in fact, having a row of all zeros in a finite element problem is another issue entirely. Okay. I'll go ahead and start the lecture on Tuesday about this because it's an important point. but just very quickly right now, having a row of all zeros basically means that your structure is under constraint. And so if you try to actually put this structure into practice with the forces in this configuration, it won't be able to hold that configuration. It will actually try to find a new equilibrium that's actually stable. Okay. And so this is a very common problem in ANSYS as well. And so in ANSYS, if you've been in 410 before, probably one error that you're familiar with is called the solver pivot warning. Okay. This is the solver pivot warning. So this is basically telling you that you need to add more constraints to your structure, right? So the way that we're going to do that here is we're actually going to change the problem. And so we're actually going to change that roller support to a fixed support to kind of properly constrain. And once we do that, then we can actually solve. Okay. But it's important to recognize in situations like this, when you have an under constrained system, and so that tells you need to go back and kind of change your problem statement a little bit. Okay. All right. Any final questions on this before we wrap it up for the week? Okay. All right. So when we come back on Tuesday, I do want to revisit this. This is a really important point. And then once we do that, then we'll move on to beams, which is our next element. Okay. All right. So thank you everyone for coming today. I hope you guys have a good weekend. And hope you guys have a good rest of your day. And I will see you guys on Tuesday. All right. Question. So won't changing the support type cause errors? So it won't cause errors, but it does change the nature of your problem itself, right? And so if you want your structure to have a roller support there for a very good reason, and you have to change it to something else, it is going to change the nature of your structure. So you're going to be doing analysis on something different. And so that's kind of so it's kind of up to you as the engineer to go back and see, is it actually feasible to change the support type in reality? And if not, is there something else you can change about the structure to make it actually more stable? Is there a way to find the new equilibrium position? Ah, yeah, that's a good question. Not easily. So it is possible. But of course, if you're going to change the entire geometry, finding a new equilibrium position is going to be an all new geometry. And so that would change how the forces interact with it and everything. So I'd have to think about that actually. If there's kind of a good systematic, efficient way to do it. See you guys. Have a good weekend. Yep. Any final questions, Brianna? I did get your email about the scholarship things. I haven't had a chance to take a look at it carefully, but I think I should have some time tomorrow. So I'll get back to you about it tomorrow. All right, I'll see you next week.